I don't know about that.
All right, 22. 22, two structural steel shapes. Got a C shape and an I shape. This is actually a W shape, a wide flange. 21 by 62, look up the area. I got 18.3. Look up the D distance, which is top to bottom at 21. Yeah?
Yeah.
Everyone get that?
Yeah.
All right, good. Look up the C shape, area of 7.34 inches squared. And look up its distance to its centroid in the Y, which is going to be in the X for the table because it's flipped. So you look up X bar and put it in as a Y distance, 0.674 inches. Because that's your piece of information that you need. Remember, we're going to go areas times Y distances, areas times Y distances. If you make this your X axis down here, then all your Y's come from there. So Y1 is literally just half of the D. What's that? Like 11? No, 10 and a half?
Yeah.
10.5 inches. Right? And then Y2 is going to be, you got to figure it out. So the way I do it is I take the I shape, which is 21. I add to it the thickness of the web of the C shape. So we're going to look that up unless somebody has it. It is TW, thickness of the web.
8.7.
0.387. So I'm going to add that to it, 0.387. So now I'm to the top, and now I'm going to subtract the 0.674. And that'll give me Y2. So there's other ways to do it, but that's the way I do it, is I just build all the way to the top and then come back down. Right? What do we get for that number? Point 387 plus, doesn't make sense now. 0.674 minus 20.713. So that's from the bottom up to this centroidal axis of this shape in the wrong position. So then you go for Y bar. And that's going to be area 1, 18.3 times Y1, 10.5 plus area 2, which is 7.34 times Y2, which is 20.713. All that is over the combined areas. 10. Oops, that's not area. 7.34. Right here, 18.3 plus 7.34. Oh. Good to go. What'd you get?
Well, not for the answer.
No, 13 is the answer.
Yeah.
What'd you get? What's the 25.64?
On the bottom,
Oh.
8.7.
Yeah, that's what I got. And that is good. So it clearly is shifted up from the halfway point of the W shape, right? 10 and a half is halfway in the W. That's what it would be if we didn't have the C shape. When we add the C shape, it shifts it up. So now we know, right, where it's located because it's symmetrical in the X direction. So the Y axis would be just half of the flange down at the bottom, be right down the center. So when we see symmetry, we don't have to calculate the X bar. That's just straightforward, right? We can locate it. But now we have the combined, and that's usually noted, like when you do it for strengths, you're gonna want that information in here. It's usually just some kind of another axis, and you would label it the x axis. That's the combined. A lot of times you'll see the individual axes of the shapes and then the combined axis. These typically are called like x1 for shape 1, and this would be x2 for shape 2 if it went all the way through. So as they get more complicated, you might want to label them just to keep things straight. And again, make a giant drawing, don't make them small. That's half the page pretty much. So. Good. Questions? I like structural steel shapes. They're like, you just pick the pieces out. Like you don't have to calculate areas. And Y distances and X distances are given to you by the shape. All right, so I didn't pick out all of the pieces of this. So hopefully somebody did, and we can just write them down. What's the area of the 360 by 110? Anybody have that? 14100. Yeah, that's like millimeters squared. Yeah. And then how tall is it? Is it 360 tall? 361. So D equals 361. And then what about the C shape? What's the area?
2170.
2170. And then what is its distance to its, be its X bar in the Y position? How much? 14.5. These are millimeters. These are millimeters squared. And this plate, how wide is it?
10 millimeters.
10 millimeters. And then the assumption is how tall is it? 361 is what I would say, yeah. All right, so that should be everything we need, right? Looks like we have to do both X bar and Y bar. Did they ask for both? Yep. So Y bar first. I guess I should number them. 1, 2, 3. So I'll do 1 first. This area is gonna be 10 times 361 times its Y distance up, which is 361 divided by 2. So that is A1, Y1. Yeah. So then I'll do my W shape. A2, it's gonna add to it because these are all solids. 14,100 is the area, that's A2. And then Y2 is gonna be half of the 360. Then I'm gonna add to it area 3. 2170. And I have to figure out the Y distance here to here. So again, I'd probably go all the way to the top, subtract the 120, subtract the 14.5, and then I have my Y3. So all the way to the top is 361. Come down 120, and then come down 14.5. 226.5. And then that's all over these areas, right? Area 1 looks like is 3610 plus area 2, 14,100 plus area 3, 2170. Y bar equals It's not that difficult, it's just a grind to get all the pieces. Just gotta give yourself a big picture and pick it out carefully. What do we get? I'm guessing, here, let me guess. What are we halfway up is one. Half of 36. 180.5. This doesn't do anything to the location of the composite, like the eye shape and the plate. They're lined up, right? So then none of that. So then this 120 shifts it up a little. It's gonna be like what? 190? What'd you get? 185. 185.52. Yeah. So you can usually estimate it like just by looking at it. Where's the mass? Is it shifted up? Then it should be above the halfway mark. If the mass is low, then it's shifted down, right? All right, so let's grind out the X bar. Try to shift it up. Area 1, 14,100. Distance, so I'll make, this will be my y-axis. This will be, so all my distances will come from here. So that means I need some more information. I need the thickness of the base or the width of the base. I think they call that B sub W. Is that right?
I got 257. That's all right.
I believe in you. So it's coming from all the way over here. So did you add 10 to it?
Yes.
Okay, good. It's 360 by 110. Metric. 360 by 110. B sub F, the base flange, is 257. So it should be 267. Is that what you said?
I just took
267 divided by 2, right? Yeah. Good. Excellent. So that's to here. From here. So that's X1. Whoops. I guess that's X2, isn't it? Looks like I'm doing the W shape first. Sorry about that. Now I'll do the plate. So I'm going to add to it area of the plate, which is 361 times 10 times its X distance, which is 5. So that's the plate. So this is area 1, X1. This is area 2, X2. Did them in the wrong order. Sorry about that. And now we need this third thing right here, right? So we need its area, 2170. And we now need the X distance all the way over to here. So I would find this distance, right? So that's going to be half of the, if you go half of the base, and then half of the web, you get to here, and then you can go half of this distance, the C shape. So however you want to pick it out, I'm going to get the C shape information. Somebody has that 200 by 17. What is it? What is the C shape? 200. Oh. And then the total height is 203. So this thing is 203 from here to here. We have the whole distance of the web, the whole distance is 267. Right? So from here and half of that, you can get to here, and then you can get to here. So I probably just line them up and say, okay, it's 10 plus, that's this first 10. And then I need half the base, so it's 267 divided by 2. That gets me to here. Now I need half of this flange or web. which is, that's a 360 by 110. P sub F, T sub W is thickness of the web, 11.4. So this whole thing is 11.4. So I'm gonna add half of that, 11.4 divided by 2. Right? Because now I'm here, and now I'm here, and now I can add half of the 203 to get to there. Wow.
I looked at it and I was like, I don't know if, like the channel, where the end of
The C shape?
yeah, isn't it called a channel?
It's called a C shape.
I see.
Yep. In the book, they call it C shape.
I didn't know where the W being, like the end of it, if it was like, if I could safely assume that was half of the C shape. And so I like,
Oh, up and down?
no,
No,
the
right and left.
from right and left,
Yeah,
or from left to right.
yeah. So it's,
No,
It's-
do you see what I'm saying? From the-
no, not at all.
from the
Totally lost.
Right bottom corner of the ivy.
Yep.
I was like, I can't say if that's half of the C shape.
No, I'm not doing that either for
Okay.
sure. I'm building this, so this location is what we want.
Yeah.
So I'm building it from here.
Yeah,
So I go 10, that's at 10. Right?
yeah,
And then I'm gonna add half of the wide flange. That's the 267 divided by 2. Now I'm to here. Right? I'm to the middle of the web. So then I gotta add half of the web to get to here. And then I gotta add half of the C shape to get to here. So that's all this.
let me be quiet now.
Does that make sense?
Yeah, I did it a little different. I'm curious to see if our answers end up being.
All right. Let me grind through this. Won't be too bad. $240.7. I'll do it again.
So,
I'm at a 10. Here, I'll just input them all, 267. Divide, so that's 133, 11.4, divide, that's 5.7, 203, and 2. So there's the 4 numbers, and I just add them. Right, because we're add, and add. Yep. 250.7. It's not what I got the first time, is it?
but,
Perfect. So 250.7, don't forget what you were doing, that's X of 3, this is A of 3. And again, all of that is over the total areas, which is that level. Total areas didn't change, so you can just use that. Where should it be? I bet it's pretty close to the center, maybe shifted right a little bit. But this shifts it left, so yeah, it's hard to tell. Pretty close to center, I would say. All right. Wow, make a lot of typos, so not super confident I'm gonna get this number. $122.96.
I got 125, 196, but again, I did it.
Anybody else get 122.96?
We'll figure that out. That's the way it's wrong.
Okay, was it this distance that we're challenged with? Yeah, that's a tough one. Like figuring out where that is not easy.
I calculated that at 235.
Instead of 226 or 250.
Yeah.
Yeah. Yeah. I just build it slowly from the left edge and just add the numbers together, right, to get to where you want to get. Sometimes you have to subtract numbers to get to where you want to get. So you just a big drawing, huh? I got 122.96. Sorry, it's off screen. That gives us the location of the neutral axis, both directions. So when we do biaxial stress, we need to calculate an inertia about those axes, the combined X and the combined Y. So next term, strength of materials, we're gonna run this MC over I. Inertia is very specific to a location of an axis. So it's not just inertia of a shape, but it's an inertia about an axis of a shape. So this shape, we wanted the inertia, which is the next chapter, we would then find the inertia about this location, Y bar, and this location, X bar. So if our goal is to find inertia, we got to go through all this first. Then we go through the whole inertia mumbo jumbo. Super long problem, and that's just like not even including the statics that you did first and not including the strength of materials that you'll do last. So they're super long problems with lots of opportunity to make a mistake. All right, good. Kind of good. Yeah, that's the most complicated one you'll ever see. Normally, we build beams out of basic shapes, right? Like in strengths, if we have a beam and we build a bridge and we build it out of two W shapes, I mean, we don't have to do any of this because it's just a W shape that we're loading, right? So it's rare we have to go through like that. Often we have to go through more simple shapes like your quiz, which is going to be something like take a 2x6 and add a 2x4 here, right? And tell me what the 2x6, 2x4, tell me what the Y bar is. Where's the axis? Where's the X axis? Where's the Y axis? Should we practice? Let's do it. So this would say locate X, X, and Y, Y axis. And that's a 2x6. And how big is a 2x6? Yeah, it's not 2x6. It's 1.5 by 5.5. And if you don't know, you can look it up. These are structural lumber. So in the back of the book, there is structural lumber. You don't have to calculate the area. You can look it up. They're rectangles, so you know where X of the 2x6 is, it's here. And you know where X of the 2x4 is, it's here. Rectangles are easy because you got the halfway point. So go for it. For 1,000 points, what's the location of the XX axis and the YY axis?
Symmetrical?
Yep, we'll put it right in the center. A1, Y1, A2, Y2, and the combined A's. I get 3.28 inches. Anybody else win the lottery? No? Did I do it wrong?
No.
So check these Y distances, 4.25 up to here. And then the Y distance here, half of 3.5 is 1.75. And then the areas, make sure you get the right area and the right Y together. Got a big mass up high, it's definitely gonna shift it up. It's actually up near the top of the 2x4. Which is good. Because we don't want a lot of bending stress in this connection, whatever this connection is, probably nails. So contractor's gonna nail it up. Right, and if we get that neutral axis close to this connection, there's no bending at the neutral axis. That's where it goes from compression to tension when you bend this shape. So. Yeah. Questions? Yeah, this is 1.5. This distance here is 3.5.
Doing another one.
I don't know, what do you guys want to do? So I could go into inertia. Or we could practice another one of these. So Dad, tell me where X bar is. Do we need to calculate it?
Yeah, that's fine.
Down through the symmetry line. Yeah, it's down through the geometric center. So if this was a more complicated problem, like if we put a hole in it out here or something, I might put my y-axis right through the center. You see that happen sometimes too. So instead of putting it way over here, put it right through the center. Sometimes that makes it easier, sometimes it doesn't. So it doesn't matter. All right, we'll do one more. This is a 2x6. And then we're gonna put on it just this chunk of wood. And we'll make this shape 4 inches by 3 inches. A little bit out of scale. And then we'll put a hole in it that is a diameter of 1 inch. And we'll locate it 2.5 inches at this edge. And we'll just put its symmetry on this piece, so 1.5. And let's just find X bar. So we're looking for that y-axis. Where is it? This is a hole. How do we deal with holes? We add them or subtract them? We definitely subtract them, both from the area, which is underneath the total area, and from the equation on top, so. Shape 1, shape 2, and shape 3. A3, X3 is gonna be a negative statement. So area 1 is the same area we had before, which was 8.25. Area 2 is just a 4-inch by 3-inch thing. So A2 is 12 inches squared. And A3 is pi r squared. Pi times 0.5 squared. Yep. 0.7854. All right. Go for X bar. Gonna pull it all from here. So this is gonna be my y-axis, this will be my x-axis. Make sure you see where these numbers are coming from. Try to find them yourself first and then look at mine, and if we disagree, then we gotta figure it out. Gonna subtract the whole. Good? Yeah, excellent. So the next step is when we do that, I'm gonna go back to the first problem, because you all have that information. Maybe I am, if I can find it. Oh, it's right here. So I'm gonna redraw this. Just kind of quickly. It's our 2x6. And our 2x4. And we have our 2x4 x-axis, which we called shape 2, and our 2x6 x-axis, which we called shape 1. I don't want to write it anymore. 2x4. Right, and then we found the composite to be at 3.28, right up in here. That we call x, and y bar was 3.28 inches, right? So we did all that work in that first one. If we then wanted the inertia, the area moment of inertia, and the reason we do, remember, is bending stress is mc over I. So if this is the shape that we're gonna load in bending, then this is the equation we're gonna run to find bending stress. We're gonna find the moment, that'll be a statics thing. We're gonna find the C value, which is the largest distance from the neutral axis, the combined neutral axis, to an outermost fiber, either direction. So clearly C is gonna equal the largest distance from here to the outer fiber is from here to the bottom, not from here to the top, that's shorter. So it's gonna be y bar, 3.28. So that's in the equation for bending stress, right? The other thing that's in the equation is inertia. And inertia is a property of this, the cross section. It is not a property of material. Doesn't matter if this is made out of wood or steel or titanium or silly putty. The inertia is the same. It is a property of its cross-sectional shape. Super important that you get that, right? So we don't need to know what this material is. We just need to know what the cross-sectional geometry is, and then we can get the inertia. All right? If we just have a 2x4 on its edge, and that's it, then that is a structural timber shape. I can look it up. So in the table, you'll see for lumber, they give you the inertia, which is great, because a lot of times we do just use individual pieces of lumber in bending, right? So we can look up a 2x4 and go across and see IX. They call it, because inertia is very specific about an axis. So it's going to be called IX or it's going to be called IY. They only give us X. The table only gives us inertia in the strong position. This is the strong position. Put a 2x4 on its side, that's the weak position. So they don't even give us inertia for that. They give it to us in the strong position. So inertia in the strong position is 5.36 inches to the fourth. That's here. IX, 5.36 inches to the fourth. Okay. If our 2x4, this is a 2x4, if it was on its side, right? This is my new axis now. We can't just look it up because it's now flipped over. So we have to have some other way to find the inertia. Back of the book, common shapes, you'll be able to find IX, IY, and another IX. Notice that this IX refers to their x-axis, which is down here. Inertia is very specific to a location. Sometimes we want the inertia at the bottom of the shape. Sometimes we want it at the top of the shape. Sometimes we want it at the neutral axis or the origin, as they're putting it here, x sub O, right? So again, it's very specific to a location of a cross section. So if we want it like right in the geometric center, that's the x sub O equation. That is I x sub O right there, base height cubed over 12. We can calculate it. So if this thing flips on its side, it's still a rectangle. We can still use that same equation. So on its side, we would say, oh, the inertia over here is base height cubed over 12. Very common equation. We use rectangles a lot. And often they don't give us inertia on the flat. So we have to figure it out in a weak position. So Ix here would be what? Base is 3.5 inches. Height is 1.5 cubed over 12. Point 984 inches to the fourth. Anyone else grind that? Make sure I didn't screw it up. Pretty sure I got it. Okay. So in the strong position, 5.36. Remember, inertia is an indication of how well the shape will do in bending. And that is a bending perpendicular to the axis that you're calculating. So if I load a 2x4 this way, it's 5.36. It's going to resist bending some. It's going to do okay. It's not a huge number. It's a 2x4, right? But in the weak position, it's not doing well at all. It's not going to resist bending well.
But it has nothing to do with physics.
Nothing to do with physics inertia. It is area moment of inertia. And the area is important because it's basically just calculating an area. And it is mathematical shenanigans. It really is. That's what the book says too. Like, don't try to put this into like velocity, you know, something you can physically like get your hands on, because you can't. It's inches to the fourth. It is merely an indication of how well a shape does resisting bending. That's it. It's also in the shear equation, the shear stress equation. So it has something to do with like, if we're going to just shear something off, inertia comes into play. That cross section matters, right? If we're going to shear something off, it matters whether it's thin like a piece of paper. This inertia, there is like inertia will probably be close to zero of this piece of paper because it cannot resist bending, right? It just can't do it. Can't do any of it. In this position, it still can't do much. Like, you're going to get almost a zero value, right? To shear it off, to like cut it with paper, with scissors, doesn't take any energy to do that, right? It's really easy shear. So again, inertia will come into that shearing something off equation too. Same with twist. Inertia's in twist. So if I take the paper and I try and twist it, twist really easy. It has no resistance to anything. Okay. But this number is in all of our stress equations. So we have to look at the cross section. That matters. That makes sense? When, like if I added this 2x4 to this 2x4, if I just straight up added it to it, and now this is my shape, this axis, its x-axis, and its x-axis line up. Agreed? Those two axes line up. When the axes line up, you can add inertias, just straight away add them. So that's great. We could take this inertia, add it to this one. That would be the combined inertia. The problem happens when the axes do not line up. So back to this thing, here's the axis, for the bottom shape. Here's the axis for the top shape. They do not line up, right? So where we want the inertia is here. To get it there, we have to transfer this inertia to here, and we have to transfer this inertia to here. And that's a pretty, I mean, it's complicated until you go through it a few times, and then you'll get the hang of it. But it's some weird distances, because you have to figure, this is the transfer distance, and this is the transfer distance. So what is this distance? Well, we know it's 328 up to here, right? And then how far is it from here to here? Half of the 2x4. So half of 3.5, 275, I think. 175, thank you. So we're 175 here. Right? And all the way up, we're 328. So we got to take 328 minus 175 to get that transfer distance. That's the kind of shenanigans we have to do when the axes do not line up. And they most often don't. But if I look at the y-axis of this shape, it's right here, correct? And the y-axis of this shape is right here. Those line up. So I could find those inertias and just add them. Okay? So that's kind of the game of inertia. The first inertia that you're going to do is just basic shape inertia. It won't be a rectangle, but it will be shaped that you can literally look up in the back of the book. Like if you wanted the inertia of a half circle, you literally look up the equation and run it, right? A rectangle, a triangle, a solid circle, a pipe, a tube. All those shapes are common shapes we work with. Obviously, if it's a structural shape, a C, an I, a pipe, that's all in the back of the book. We literally look it up. We don't have to calculate that. So you're going to do a couple out of the book that are simpler. Not bending stress, not moment of peace. I'm in the wrong chapter. Not stress and strains, centroids and center of gravities, inertias. So I believe I gave you number 1 or 2, sorry. Number 2. And I think I gave you number 3, 2 or 3. I don't remember. Has anyone looked? I'll look. I gave you 2 and 3. So 3, the X of the W shape is right in the center, and then these plates are added right in the center. So all of the X axes, whoops, sorry. Thanks, Devin. All of these X axes line up. The W shape is in the center, and the plates are in the center. So you literally find the inertias of the 3 shapes, the 2 plates and the 1 W shape, and add them up. This one, you're going to look it up. These 2 you will calculate. Rectangle, base, height, cubed over 12. Pretty simple. You can handle it. And 2 is just triangles. And you'll see their inertias line up also. And a triangle equation is here in the back. Even though it's the off-center triangle, it still works for all triangles. So that's blurry as heck, isn't it? There we go. Triangles. And equations. We are launched into the weekend. That's exciting. You all seem so excited. Love it. You do?